Hello from Dendrite Digital in Anaheim, makers of the Virtue Data Processor, and ZipBits, the website made entirely of human-readable JavaScript, HTML, and CSS. So here we are in Vivado with our files all queued up. This is something that was giving me a problem earlier. In the process of figuring out where all the files should be assigned, I turned off the simulation source for this file here. And let's look at that file right now. So here's the file. I commented out the top part and allocated the bottom part. And this is for displaying hex codes on a 7-segment display. And it's got some more problems with it, but we're not going to discuss that right now. But see if you can find where the problem is here. It's in these bits. It's hidden in here somewhere. And it's common anode, so the zeros are actually on and the ones are actually off. Common anode. So, yeah, anodes are negatively charged, but they're thought of as positive for historical reasons. So when the anode is on, then and the bit is on, it's off. So look through these binary digits and see if you can spot where the problem is. It's very hard to spot in bits or in simulation, but we'll see where that problem is later. But just see if you can figure that out. And then here in the test fixture, all I'm doing is I'm setting up the test fixture for the hex decoder, unit under test, the name here, and the corresponding name there. And we just do that for each of the parameters. And actually they're input-output declaration. And then here we just assign 0 to data, wait 100 nanoseconds, and then every 10 nanoseconds we add 1 to it. And so it just cycles through the 16 permutations of the hex counter. And then this was the error I was getting because of that checkbox I mistakenly clicked. And so to find this file is rather difficult. Let me see if I can do it. So it's got a new value, so I'm going to close it. It's not going to be the same later, but let me see if I can find it. Excuse me, I'm going to sneeze in a moment. So if we go up to simulation, and down here in the simulation folder is simulation log, and here's the elaborate log, and that was the one that was giving me trouble. See, it's been fixed here, but I redid it. So if I go back to Vivado from Atom and we run simulation, yeah, there's all kinds of vexing problems that can pop up if you're not really careful. even if you are really careful, there's still going to be some things that were overlooked all throughout the programming process. One line of code can cause a disaster. And here we go. Especially when software gets complicated. So it looked like it worked anyway, without the file included in simulation. But yeah, I don't know how that happened. It just worked this time. And so if we just click this bunch of arrows right here, it puts it into the right size. And as you can see, all the segments are turning on and off in a particular pattern. Counts to 15 and then it starts over. You can see that pattern repeating here, and a corresponding pattern appearing on the LEDs. So that looks good, but again, there's a problem in here that we haven't detected in the simulation or the code. I want to see if you can find it before I show you where it is. So then let's since this is working right, and my little counter is pretty simple, let's go here. So here's the hex decoder. There's some sort of problem in here somewhere. And then here's the little counter thing. I'm going to uncomment it. Hold on. Oh. Then we need to get rid of this right here. And then what? All right. Everything's activated. And so all this is doing is it's cycling through each of the digits. So when bit 20 and through 18, 20, 19, and 18, it takes this number, 3-bit number, and it selects one of these 7 switch statements. So it cycles through these 0 through 7, and then it starts over 0 through 7, and it just assigns to the display. The display code goes in here as the hex digit, and we're just selecting another a 4-bit segment of data, and every time counter 21 has a positive edge, it adds 1 to data. So it should just be a 32-bit counter, counting up 1, 2, 3, 4, etc. And it's going to be doing that pretty quickly. So if we take the clock, let me change this. This seems to be CLK to match the file. And so we just cycle through this, and so this is simple enough that I think I can get away with not doing a test fixture, make sure it's doing what it's supposed to. Simple enough. I've tested it before, seems to work sort of. I kind of shuffled these digits around in the wrong order before, but I'm hoping this will work. So 0 through 7, 0, 4, 8, 12, 16. So a little 4-bit number for each one. Goes in as the display, comes out as the segments. And then that's communicated to through the out the outputs. Now, something we haven't done is looked at the constraints. So let's close this. And now let's look at the constraints file, because it's going to have something going on there. Constraints. Now it's the right board. And yeah. So yeah, see, as I suspected, CLK and not clock spelled out. And then here we have the switches. We're not doing anything with them yet. And then we have LEDs. And the thing about this is these are the little individual green LEDs associated with each of the 16 switches on my development board. And these are RGB LEDs. Here's the 7-segment display, and you can see that they're not commented. Each one of these is not commented, and so we got segment 0, segment 1. Now these correspond to A, B, C, D, and we should look at the Wikipedia on the 7-segment display. Now here's the decimal point for each one of the displays, 7-segment displays. There's a decimal point associated with it. And then here's the anode. Now remember, anodes are thought of as positive in electronics. We got it backwards ages ago, and we're just continuing with that same idea. So anodes are negative, but they're expressed as positive voltage. So a 1 as an anode means 0. Yeah. And so these are this is the numbers 0 through 7 in the code, and I'm just lighting up each of the 8 digits one at a time with a common anode for that particular 7-segment display. And these are the actual segments. So we have 0 through 6, 7 segments, 0 through 6, and a decimal point, which we're not using. And we are using all 8 digits of the display. And so this is where you find out if you're using an anode or a cathode. Your constraints file should tell you whether it's an anode or a cathode. And they've done that here just by using the letters A and N. And so you have to have a common, and you have to have the 7 segments and decimal point if you so choose to use it. And then the rest of this is all disabled. So get your XDC from your board maker, whoever that might be, because without this you're kind of lost as to what's connected to what. You got to get out the logic probe and write a program on the FPGA to go and turn on and off each of the LEDs or each of the outputs. You know, it's such a headache. I don't know. You're gonna have to do something somehow, and so if you like had it cycle through each thing and in it every second, you know, you might be able to figure out what's connected to what. just have it, and by timing you can go, oh, that's that input, and that's the other input. And so yeah, you could if you don't have your XDC, especially if you're unfamiliar with FPGAs, you're not going to get anything done for a long time. You're just going to be looking at the unit and trying to determine what pin is where. And you could write a program that would access all the outputs of the FPGA and just go through them one at a time, turning them on and off. And by the timing of it, if you precisely time your FPGA to blink it at for a second and then go to the next one, blink it for a second and go to the next one, and you time it right, you could match up the flashing LED or the switch or whatever is going on by how many seconds have elapsed, which is crazy, but possible. If you don't have your XDC, yeah, and then so let me switch this over to doing. Let me switch this over to doing simulation from simulation. Yeah, see, there's no errors there. And let's do synthesis. Come over here to synthesis, run synthesis, and let's hit OK. And this takes a while, so I'll see you shortly. So here we are, and apparently I missed something. So what did I miss? Let's look at the messages. Clock is not declared. Oh boy. We changed it in one spot, but not another. That should be easy enough to find. Hex counter line 30. So if we go here, we go to hex counter, and we go line 30. Clock! No! I hate that it's like whoops, not return, but delete. There. So that's all it was. And these errors pop up all the time. So let's try again. Gotta wait for it to update. Everything's gotta be just so for this Vivado to work correctly. Now that it's done, we can go to log and synthesis, run synthesis. And it's cleared the display. And this is the part where sometimes it just doesn't display a thing. It just sits there and never goes anywhere. So that's the first part that you can make sure that it needs to work. It'll drop down a line. There it did. Drop down a line. And once it does that, it usually finishes. I'm not saying all the time, but it usually finishes. And sometimes it'll display all of this stuff and just hang on exiting Vivado, and it just never quite finishes. Just spins and spins and spins forever. I've had it compile the whole. I've tried to compile it all the way from synthesis through generate bitstream, and I'd leave for an hour and come back, and I'd see it still stuck on synthesis. It says exiting Vivado for synthesis, but it just never goes on to the implementation or generating bitmap. It just gets stuck. But, you know, it's nice to see something, but it's not always an indication that everything's working fine. And if you end up in that situation where you're stuck on synthesis, one method is exit Vivado, delete everything but your source code and the project file, the project app, or the main document for the process, and then start fresh. I've been in that situation a number of times with Vivado, that you have to treat it kind of gently, let it finish most of the time, because that's when you start getting stuck. Is when you interrupt it, and sometimes you just can't get away with interrupting it. And in that situation, you gotta delete all the files that aren't necessary to the project and start fresh. It's not too much trouble, but sometimes you have to exit Vivado before you can do that, because a lot of the files kind of lock it up from deletion. They lock out deleting the files because the document is open in Vivado, but nowhere else. And you gotta close out, or at least get to the main screen, the main intro screen with the menus, and delete all the sub files. The simulation and the runs and the support files and all of that stuff, and keep the main app, and keep the project, and keep your sources, and just start fresh. So here we're getting a little further. Yeah. I recommend doing the UTT, the unit under test, because this takes so long that you're wasting a lot of time waiting for it to finish. That it's important that you make sure you've got everything covered that you can possibly figure out in simulation before running the synthesis and the implementation and the bitmap, bitstream, generate bitstream. It's a lengthy thing. So save yourself some time and do a unit under test. Now, I'm not sure that this is going to work the right way. I've tried a few things before and had it working, but here it's just crazy. So on the advanced end, working on making my own processor. Currently, it's 24-bit. It's got 32 instructions. All the favorites like jump on, carry, clear. I'm using jump because I have a 24-bit instruction, and I've got like 18 bits left over, 19 bits left over. So branches stop making sense. Relative branching from the program counter. If you can jump anywhere in memory with just one instruction, hey, now we got run implementation. So let's go and do that. I imagine it's going to show us what I was worried about. Let's look at messages right now. Set property expects at least one. Oh man. So we've got something going on line 269 of the XDC. It's probably what line was it? Line number 269. 269. Yeah, see? Here's something going on. Yeah, what is this? Oh, it's a PMod. So, here, yeah, that's for the keyboard. Let's fix that while it's compiling. Whoops. I don't want this. That's crazy. Why is it doing this? So, yeah, and this one here. So, those were a problem. So I wonder what it would do if I tried to run that file with those two ports uncommented. It'd probably go and you know, not access them. But it might just crash the it might just spit out the file without. Yeah, see, it's exiting already. So it's probably got like error somewhere. Didn't flinch. Oh, that's synthesis. Let's look at if implementation is printing. Now see, it's into op design. It's done initialize design, and nothing is showing up in this window. So let me cancel. So it's still okay. Let me see if I saved that file. Haven't saved it yet. If I save it, it's probably going to start all over. If I save it, it's going to start all over. And let's go look and see if it... Yeah, out of date. So we got to start all over. And come over here to run synthesis. I'm trying to do this uncut. You know, maybe prepare some code, because it's just pointless to watch somebody else typing. It's better to have the code all there and be able to discuss it. Yeah. So this is working, and we go back to the code, and we got. So yeah, this is just. All we have is this set of counters. Counter is for the display, and data is what's going into the display. So we have 32 bits of data, and we have 32 bits of counter, but we're only using the first 21 and using the top 3 of that 21 bits to cycle through the displays. Each hex digit for the display. So display is passed to this hex decoder. So it takes the 4 bits of display, converts them into the 7 bits of segment, and then segment goes out to the board, out of the FPGA to the 7 segment displays, and also the anode. See, we turn on all the anodes here, and we turn off just one of them later. And this is with blocking assignment. It's a little like C. C will do this, but if you have non-blocking with a less than symbol before the equal sign, that's called non-blocking in Verilog. If you have non-blocking, the last value that you set it to is what's going to stick. It doesn't matter what came before or after, only after. It's going to be the last thing that you set it to. So you could probably do this with non-blocking, but I've got it here for you beginners in Verilog. I'm using blocking assignments. So yeah, there it is. And you generally only can do non-blocking with a clock signal, one edge of a clock in the always block. And so yeah, there's not much to say about this. This should be real simple to work. Now this still has a bug in it, and have you found it yet? Have you found the bug in these bits? It's sneaky bug. So here we're getting a warning. Reference run did not run incremental synthesis because the design is too small. Yeah, it complains about all kinds of stuff. Most of the time, it's, for code that hasn't been finished, yeah, you'll get a lot of errors that way. But if you've tested it and you've run it through a test fixture or a test bench, and you made sure that it looks right and that everything's initialized properly, then you can advance to the synthesis. Otherwise, you're just going to be spinning your wheels. You can go through the synthesis and you'll find plenty of things that you didn't catch, but it's slow. And see, all this time we've been talking, it's been chunking away on just synthesis. We got to get through implementation and then generate bit stream. But yeah, it takes a while. So here it's finished the synthesis, run synthesis, it's over with. It's asking us if we want to run implementation. Now, let's see if it'll show us the status as it's happening. The way you do that is you go log implementation. Here, now you look up in the upper right hand corner, and here it says there. So it's got to drop down another row, yeah. So it's going to print it out. It's going to show us what the implementation is all the way through. So here we finished the implementation. It has the bit stream to generate. As you can see, mostly error-free. No errors, no warnings, no critical warnings. 83 infos. That's a good score right there. So in implementation, we didn't have any problems. And then here in synthesis, my mouse button. There we go. So this has, yeah. So if we go to design runs, we can see how long it takes this. So I started at 542 here. That took 5 minutes 10 seconds. An additional 6 minutes 41 seconds. So all that together, 11 minutes and 50 seconds. So a lot of time waiting for this to finish. And we haven't even finished the bit stream yet. So that's going to take a while. It might be shorter for a smaller FPGA. So if you're doing something little, you can do on a small FPGA if you have one available. It's probably faster to do all this. So the little projects you can put on the little FPGA and get it done a lot quicker. I've noticed there's a significant difference between the T100 and the 200T. It's like double the length of time. So that would be like 20 minutes if I were to do it on the Arctic 7 200T. And here we are. Yeah, this will say 100 at the end of the 100% at the end of the implementation. But I've noticed if you write the bit stream, it'll bump it down to 83 until it's finished with the bit stream. Crazy, I know. But all this big software, they can't think of everything. So here it is, finished writing the bit stream, and we have a choice. Do we want to look at the implementer design? It seems to be all black here. No, can we? Yeah. See, these are all good numbers. All the worst negative slack, total negative slack is 0. Worst hold slack is positive. Total hold slack is 0. So these are good numbers. If these are red here, it's not too much of a problem, especially if it's small. But you get over here to the total pulse width slack, and that's a negative number. You gotta fix something. But here we're good. So I'm going to go straight into open hardware. And this takes a bit of time. Maybe a faster PC, I don't know. I can't afford a faster PC. So here we are. Auto connect. If I was an employee at Apple, they'd fire me for watching this stuff. I don't blame them. When I get my processor working, I'm gonna do it so that as you're typing it in, it's converting it to machine language. A live compiler that would just wait for you to type it in, and as you're editing it, it shuffles it around and fixes it and tells you if you've made an error as you're typing it, instead of this crap. And we're gonna see something. We're gonna see something on those 7-segment displays. And is it connected? Is it gonna work? It says all fine here. What is taking it so long? Come on, work. There we go. Yes, and it's counting. Awesome. But it's refreshing now. Takes it forever. My counter's already up to 290. A, B, C, D, E, F, G. Nope. 300. So when this, finishes, I'll give you an idea of how nifty that little counter works. Here we go. Just give it a moment. So here we have the counter. I don't know if you can see that clear enough. It's a little too bright, isn't it? But, it's counting. And unfortunately, we didn't catch a bug until right now. See, E looks like 3. Let's see if we can wait for the 7 to turn into an E. I don't know if you can see that clearly or not. It's got a lot of contrast. That's 8, 9. A, come on. And yeah, see that E. That E looks like a 3. And real hard to catch in binary or in a waveform or whatever. We got the E and 3 the same. D, E. It looks like 3. So there's one C. But doesn't that work nifty? All in hardware. So this could go really fast if it needed to. But, look at that digit on the right. It's just going. Yep. 1/10 of a second or so. Somewhere in there. 1/10 of a second. Well, now it's at F. Went right by it. All right. So let's go track down that E3 bug. Let's go find it. So let's close Hardware Manager. And this takes a moment or two. Everything running so slowly on my Atom processor. My little $100 PC. And if we go here, and we go, let's get the log window down lower. And we look here. And we go out to Atom. And right here, this is the wrong 2. It should be over here somewhere. I think we have the A and the A and the G in the wrong place. Should be here, these 2 right here. 1, 1. We go over here and put a couple of zeros. So they're on the other side of the 7-segment display. So that gave us the right number. E, 14. C is 12. It should look similar to C. Yeah. And the difference between C and E is that that one digit right here. See, that's turned on. Actually, that's turned off. That's the middle line is G. So it goes LED A, B, C, D, E, F, G. So it should look like C, but with the middle line included. And like I was trying to say before, this is a common anode, so all the bits are reversed from what you think they might be. That's where those problems come from. So here we are. Let me close a couple apps here. On my Mac, you might not be able to see that. So here is what I've done. I've recompiled it. So if we open Hardware Manager, actually I need the other mouse, not the Mac mouse, the PC mouse. So here we go. And this takes a while because it just does. I wonder if other FPGA designs are a little more turnkey without installing all these gigantic apps that take forever to compile. I don't know if the Intel variety of FPGA is any better for this. Xilinx versus Intel. AMD again. AMD owns Xilinx now. Isn't that crazy? It's all going into one company, and then we're not going to have competition for the public dollar, and then we're just going to end up all slaves to the government. There'll be the ruling class that make the technology, and then there'll be the serfs that just consume the technology with no job. You know? Yep. And this is going to take a while. Here we go. And a little while longer. Da 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 da. See, we're still unconnected here. It says connected there. Open. Status. But this needs to come down and say open program hardware. There we go. Program device. I think I'm on video G. G-H-I-J-K. I don't know. We're almost there. Is it me or my PC that's so slow? So we're going to try again. Try our program again. go. And does it display E correctly now? Yes, it does. Now E looks like an E instead of a 3. I'll show you. Just give me a moment. So here it is, ticking away. And does it show E correctly? Yes, it shows E correctly. All that time and coding and waiting and yeah, FPGAs aren't for the impatient. If you have infinite patience like a computer, then maybe the FPGAs are for you.